Alright, going live again, and in this video I'm going to be improving the firmware for this Flying Berman crane control system. I do not build the crane myself, but I make the electronics for the crane, and it looks like this. If you haven't been following my video series, I've been developing this motor control board, which accepts many different inputs, and I actually have the same board in the control panel as I have for driving the motors, and they communicate using a CAN network over this yellow cable. When I'm done with this project, I'm open to taking on contract work or doing a crowdfunding campaign. We'll see what I'll do then. I think it will be fun to actually do a crowdfunding campaign, because with crowdfunding you can actually have a bigger say in what I'm doing, and I could make some project that could be interesting for all of you watching, and you could also maybe like pay $1 a day or $30 a month, kind of like a pay as you go, and if you're not interested, you just stop paying. If you continue being interested, you kind of keep me going on a crowdfunded project. And it's going to be broadcasted live, and you'll see everything that I'm doing, and you'll have full access to all of the things that I produce every single day. Anyway, we'll see how we do that. Today I'm going to be continuing work on this firmware, and I will be going over the firmware in full. I have a list of symbols that go into the firmware. I've marked the ones that are part of the STM32 libraries with blue, and the rest of them, or most of the rest of them, are the symbols that are part of my code base. So let's start with ADC1. This is a variable that is defined in the ADC driver. I'm going to go to the ADC driver here. This variable is located, let's see. This is a global variable in order to make the ADC1 accessible from the interrupt handler. And things I want to check here is to make sure that any kind of interrupt access to this variable is secure, that there is no possible race conditions, no concurrency errors, like no possible concurrency errors, things like that. So just kind of looking over the code and seeing what we can improve on every single method in the code base that goes into the firmware. So I don't care about any other code that doesn't go into the firmware. I only care about the methods that actually go into this firmware. So let's see. First of all, I'm going to call this variable with an underscore, because that's what I use for all of the variables that are not visible outside of this file. So we have ADC1. Now we have ADC1 used here in the interrupt handler, and we have ADC1 is set here, and then it's not used anywhere else, or actually, yes. So this is right. So the same handle is also passed to this method here, and let's see. So what I want to ensure here is that this mem copy cannot happen like in the middle of copying the previous ADC reading, because I want to have all of the ADC readings, like, even though it doesn't really matter if I get like half of the ADC readings from one PWM cycle and half from the next PWM cycle, they don't change that much. But I still want to have kind of a full set of readings without having any interruptions in between. So what I'm going to do here is I'm going to disable the ADC interrupt when I'm doing the reading. Let's see. This part of the code basically just warns of any overrun, and this is what they say in the datasheet you should do if you detect an overrun. Normally we shouldn't get any overruns because we're using DMA, and it's going to be happening on time. But it can happen if I, for example, trigger the ADC manually, using the software trigger for some reason, but that would be a bug. So we could just print to the console ADC overrun. In terms of copying the value, I'm going to do like this. I'm going to do nbig rq channel cmd ADC rqn disable. So what this does is it actually disables the delivery of the interrupt. It doesn't disable the actual interrupt that is asserted by the ADC. And that's very important because if we have if we disable the ADC interrupt, we may actually miss readings because the interrupt will just not fire. If we, on the other hand, disable the interrupt controller interrupt, so we're just disabling the delivery of the interrupt for a short while, then once we enable this interrupt on the interrupt controller, it will actually be delivered if it's pending from the ADC. Enable it here. And is there any other place here I have? Yeah, in terms of the command line interface, it's maybe we can improve something here. It's a number of conversions. We have different flags. I could actually print the flags in one, just like this. Status is going to be if this one is set, then we do I want to see what the code is for inverting. Let's see. Or invert the color on the terminal. Just make it a little bit more compact. This is not really critical. This is just a command line tool. But yeah, while I'm at it, I could might as well improve it a little bit. So what is this? Maybe I could just Right, so if I make it black and white and then just reset the colors. So anything that's enabled, like any flag that's enabled, is going to be like this. Kind of like this. I'm just doing it because it's fun. I should really be doing other things. I shouldn't be doing this. This is not very useful. And everything is read from ADC1 because that's the master ADC. Okay, done with this. No more of this stuff. By the way, yeah, of course, this needs to be a space there. Okay. I'm not using the DMA interrupt. I set the clocks. Let's see. So I could actually mark this as done. ADC CMD done. ADC device init and device register. These are internal functions, so they're done. DMA configure them. DMA configure. now this is just a simple direct installation of the DMA channel. This is fine. ADC drivers. This is actually the internal variable that holds a list of all of the ADC drivers that belong to this class. ADC find by node. This goes away. ADC RQ handler. Trigger also goes away because I don't want to trigger the ADC manually. Does it? Just because it's part of the interface, I will leave it here, but I will not allow triggering this ADC. Because this ADC is running automatically. Actually, it should be running automatically in every case. It shouldn't be triggered manually. ADC is so tricky to create any kind of generic code for because it's so specific for every application, especially the timing when you need to trigger it. Okay, this is code from STM-F1. DMA1 is not something we need. Comment in it. External trigger. This doesn't seem to matter. I've changed the external trigger to be set to the external trigger specified in the device tree for every ADC, not just the last one, not just the ADC one, but all of them. And that seems to work. Continuous mode is disabled. Multi-DMA request. This actually starts a new DMA transaction when the previous one is done, so this is important to enable. And end of conversion on each regular channel is disabled. It's actually enabled by default, but I have to disable this because I'm using the ADC interrupt to copy the data, and I don't want that interrupt to fire every single time. Every single time an ADC converts one conversion, I want it to fire when all of the conversions in the sequence have been converted. Channel config. This basically sets all of the channels. Initialize DMA, or rather deinitialize DMA, and then DMA configure. Actually, this should be part of DMA configure. Because this is, yeah, this is definitely should be in here. Let's do like this. Actually, I'm already calling dinit, so I've been calling it twice. So it's stuff like this that you notice when doing a review. So I like doing reviews. Let's see. But I'm probably going to find more serious stuff as well. So the interrupt priority, I set it to maximum priority, which I think makes sense for this interrupt. The thing is that if I set it to maximum priority, I'm not able to use free RTOS methods. Like I cannot call, for example, any queue methods to push something into queue, or any event methods, because this is below the maximum priority, or rather above maximum priority, because the lower value means higher priority in this case. So DMA configure, configure the interrupt, and then so just doing things in sequence here. I shouldn't be registering the device before I'm done with it. I should do this last. ADC device init, ADC device register. So enable DMA on ADC1, enable all of the ADCs, and add the command as well if console is specified. Perfect. So this is done. RQ handler is green. ADC ops is a variable that's specified here. So ADC ops is supposed to be static const in this case. Perfect. It's static const. And next is this address. So this, what is this variable? What is this addr? Let me check. Let's see. I'm gonna check the map file. What is this addr? It doesn't even seem to be there. What does it mean if it's small t? I'm gonna see if I'm gonna check the data sheet. Or the manual page for NM. So from my Python script, I actually went to using NM because I figured it actually does provide precisely the kind of output that I need. Let's see here. Little t. The symbol is in text section, but this symbol has no address. So that must mean that the symbol is actually undefined. Maybe this is some kind of extern somewhere. I could do a search. I can do it actually like this. So maybe I can find something. So this is not I'm not sure why this is gonna just return a lot of things. Maybe I could search for something like this. Let's see, uint. Is there some kind of static addr or something? Anyway, this variable does not have any address, so this is so this is a symbol that is like I think it appears like unused if I use objdump. Could actually try. Let's see. Interesting. It does have. Oh, it doesn't have any length. It does have an address, so that's the thing. So it's a zero length symbol. Could I get? Oh, actually, I could do like this. I could use GDB to get the line where this is defined. Let's see. Let's see. this is actually defined in init. And it's defined on line 47 of fault. And apparently this is a globally visible symbol. Yeah. Okay. So this is other is actually the address of the hard fault handler stage 2. So I've added this code in order to be able to dump the program counter when I get a hard fault, and so far it's been working really well. So whenever I get a hard fault, I end up here with GDB, and then I can just print the program counter. But this other variable is here, and it's basically like, is it not possible to just call hard fault handler stage 2 directly here? I don't know. Let's make this. Does it need to call R2? I don't know. I'm not very good at this Cortex M assembly, so I don't really care. I'm going to make this an internal symbol. Just mark it like that. Let's do like this. Okay, so this can be safely just marked green. And next we have the analog stuff. So analog device init, all of these functions, they're default auto-generated functions. So I can just directly mark them as green. Analog drivers as well. Analog ops. I could check the analog ops. I think. Let's see. This is going to be defined in different files. So I could do like this. Struct analog device ops. And then I get just a handful of them. And it's basically just these ones. And the timer. The timer has analog device ops as well. But I am not using, which one am I not using? Or do I have another one somewhere? So apparently I only have 2 of them. So which one is not included? Okay. Yeah, never mind. All of these look good, so I can just actually I could do like this because I cannot include the address into my CSV file, because I want the CSV file to reflect any kind of changes that I do to any symbol, and addresses would usually change a lot. So even though the symbol may not have changed, the addresses would usually change. So I don't put addresses into that file, but I could still have a look at the addresses like this. Let's see, can I get... yeah, I'll just do an M like this. And analog ops. Can we... Alright, actually all of them are there. The one that I thought was missing is called Tim Analog Ops. Yeah. as well change this to analog ops. Or actually, I'm going to keep this team analog ops, and I'm going to change the other ones, so it's easy to find, easy to figure out where they belong. LP 55231 analog ops. LP 55231. And the other one is this one. MCP 461. The third one is somewhere in the end of the file. Any on, what is this? This is in text section. Where does this come from? Let's search for any on. It's located there. And let's see. No line number information. Okay, this is probably something that GCC has generated. And this one I'm going to remove, I think, because this one, I remember, it's probably in the file where I initialize the clocks. Let's see. Crap. I think that my computer is suddenly getting slow, so let's make sure that it doesn't crash. Okay, this is actually defined in the RCC. And it's also defined here, yeah. Okay. So this is static as well. So this stays. App is located in data. I wonder if app is actually here. It's like this stuff. Yeah, static. Create the init task, and actually this is completely unnecessary because this is just the init. The only purpose of this is to fork out into a task before initializing all the device drivers. Could actually thread suspend. I could suspend this thread as well. I'm gonna check if I can actually do this. Okay, so e-task suspend. So actually, I don't need to do this. I can just, because this is like a hack. I mean, this thread will wake up every second and consume CPU power. So better do like this thread suspend. And this thread will be suspended until the application restarts. A little bit of a waste in terms of stack memory. And these ones I'm not using them, they're just here so that I can see if anything else uses them. For example, if I do a printf, I'm probably going to end up in write here. Let's see. And then I can remove the application, this is not necessary. This is just... Do I actually get here? I don't think I actually even get here. So what if I just do like this? Return 0. It's never going to get here. And panic is just a while loop. Task switch hook. This is an interesting hook. It's called every time a task is switched. So it's possible to like send out stuff on the debug interface. And what I'll do now, I'll go to the thread implementation and I'll do like this. Just a wrapper for the FreeRTOS functions because I want to be able to compile this against pthreads, and I have a different version for Linux. So I have a Linux version here. It's quite out of date right now, but it's usable with a few additions to it, and it basically expresses the thread interface in terms of pthreads. So. This one is removed, and the EEPROM driver. This is like the simplest memory driver ever. I should be naming this as the same way as I named the drivers. And in this case, I have to have a lock here, unless, yeah, I mean obviously I won't want to be writing to this EEPROM. Yeah, I'll add a lock here because I may be adding block writes later, so guys, I'll have mutex. And then this will lock thing is that I do already have a log, and I just see what else is shared here. It's like nothing else is shared. And this basically just reads the IDC device. And remove would be like memory find by ref t node. And okay. All of this is okay, and I'm gonna remove that log for now, because I don't need it. Okay, so this was dev instead of mem. So I have to use devs here. Okay. Base fix blanks. What is base fix? Yeah, this is some kind of libc stuff. Blanks as well. Yeah, because I don't have any reference to this. Buff. This is interesting. So this is static variables, and generally they can be a problem if multiple tasks call a function that uses a static variable inside the function. And they are difficult to find, so I'll have to search for this buff variables. Let's see. So I have one in the serial, I have one in the console, and I have, let's actually search for char. So it's console and serial. It's just two. Was there another one somewhere? Yeah, and in main. Buff, static cube, buff. So let's have a look at all of them. yeah, this is basically just test code, so this is not, this can actually be removed. It's completely useless code. And the console is using buff. Yeah. This should definitely not be static. And this buff is used for print k, which is actually wrong, unless I use this. Yeah. I should actually place this. Oh yeah, this is completely correct. And then I lock these variables here, so I essentially end up with a thread safe function. Okay. Let's make this print k. Right. So all of the buff variables are okay. CLlock is part of the C library. Moving on to the can interrupts. And I could actually print k. That's fine. Panic is fine. Moving on to the canvas. Yeah, all the interrupts are fine. The other functions I'll review when I get there. Can command. is can CMD somewhere else. Maybe it's in main. No. Oh. Let's see. Yeah, it should have been in main. There it is. Okay. And this basically doesn't belong here, so this goes into the CAN driver. Or into a more generic CAN. Actually, yes, this is just part of the interface, so this goes into the CAN driver. Okay, let's see. I'll just read all these variables directly, and probably also show more information. Let's see, main C is here. CAN CMD. Get path, I think, returns the. Let's see. This kind of becomes the full path of the node, but can I perhaps get just the name of the node? Node name. Okay, so we could get the name like this. What was it? It was like get name? Oh, what was the actual entity? Let's see. get name. Okay. So just entity get name, entity node and null. So this should register the CAN interface with the name. I don't need this crap, so I'll just go ahead and give the pointer to the counters. I'm almost curious to see how this works. Where did it fail? It failed here. Could it be like RQ disable? Let's see. Oh, it's disable RQ. Right. So because I have code for different architectures in the same directory, I sometimes get the wrong tags. Disable RQ. Does this work? Yeah. And then enable RQ. So I'm going to add the console device. Console find live ref empty node console. All right, and this will be the last thing for today. Can1 is going to have console pointing to details. Alright, it's time to test the can. I still have this. When I have stutil running, I cannot flash the chip. Okay, and let's see, you have can 1 and can 2. Cool. Can 1 info, can 2 info. Alright, that's it. That's it for this video.